Welcome to our today's mathematics class where we are going to look at rounding decimals. Previously, we have seen the issue about fractions. We have seen how we can arrange fractions in order of ascending or descending. We came to the decimals again. We looked at how we can arrange them in the order of ascending or descending. But this time round, now we want to concentrate on decimals and see how we can round off decimals. Looking in our daily life currently, we find that decimals are used across the world. And mostly when you look at currencies, we find that it has been very important to be rounding off the number of decimals when it comes to currencies to 2 decimal places. Also, I want to give a good example is in athletics. We have the world fastest runner, that is Usain Bolt, whose world record stands at 9.58. Now, you realize that they rounded off his time to 2 decimal places at 9.58 seconds. So this is rounding off. Now, with this other side, before, as we said earlier on, before the decimal point, what we have is a whole number. And after the decimal point here, what we have this side are decimal places. So when we are rounding off, we want to know how many decimal places are we going to consider when writing down a number. So rounding off has been done and used in many ways. So how do we approach rounding off, especially when it comes to carrying out the mathematics? Now, first we need to know the mathematical symbol that is used to round off or to approximate. So we use some parallel wave lines, which simply means approximately. The sign that we have there stands for approximately equals to. Simply used to indicate a given value. Now, to round off a decimal, we need to look at some steps. And first, we need to cut the number required. That is, the first thing that we need to look at is cut the number after the required decimal place. Cut the number after the required decimal place. And then to determine whether you should round off upwards or down, we shall consider the next digit immediately after the cutoff. The moment you identify the number of decimals that you require, I want to give an example of 15.6327. This is the number that we have, and from this number, if they are asked, if they ask us to round this number to 2 decimal places, then the first statement we are getting here is that cut the number after the required decimal place. So 2 decimal places shall count from the decimal point 1, 2. Now we shall have a line there. That line is telling us that this is the point at which we are cutting. After doing that, then we shall now consider the next digit after the required number of decimals. In this particular case, we are looking at the digit that I'm calling 2, this digit here. So the digit that we have here is the one which is going to determine if we are going to round upwards. This digit here will decide whether we shall round up or down. This digit, we call it a critical digit. The digit that we have 2 is called a critical digit. And as we can see, it is the one which will decide if at all this 3 will be rounded upwards or downwards. Now, let us now come to the critical digit that we have. What does it determine? Given that if the critical digit is below 5, if the critical digit is below 5, or just say less than 5, that is to say if it is 0, 1, 2, 3, and 4, then the situation here, we shall round down. If the critical digit is below 5 or less than 5, that is either 0 or 1, 2, 3, up to 4, then you will round down. Looking at the situation that we have here, the critical digit here is 2. 2 is less than 5. So if we had been asked to round off the number we have to 2 decimal places, then from the required decimal, looking at the critical digit being less than 5, then we shall give our answer as 15.63. So this remains. We shall not consider other decimals that existed as long as we have the required number of decimals and we have seen the critical digit is not adding any value to the required decimals. However, when we have the critical digit being different or being if the critical digit is greater than is greater than 5, that is 5, 6, 7, 8, 9. This is greater than 5, then you round up. You will round upwards, or you round up. So the situation that determines whether you round up or down is if at all the critical digit is greater than 5. For the situation that we have here, 2 is less than 5. But let's see, supposing the number we had was different, so that we have 6, 3, 7, 1. And then we are asked, round off this number to the nearest 2 decimal places. Then we shall count 2 decimal places, that is 1, 2. Put a line, then you now circle the critical digit, and then consider it if it is above 5, then you'll find that 3 will increase by 1. We are going to round upward, so the answer will be 15.64. So you'll notice that 3 has been rounded upwards. So anytime you're rounding off, any other decimals that existed in the original figure are left out. We only consider the ones that we have. Let us look at a few examples. So we have the question, the following numbers that we have, the following numbers of decimal need to be rounded to 2 decimal places. Draw a line where the number must be cut and then circle the critical digit. A, 23.5398 and B, 1.75137. Now to tackle this, as we have been told, there are 2 conditions we must observe. One is simply drawing the line where the number must be cut, and 2 is circle the critical digit. In our solution here, at A we have 23.5398. We need 2 decimal places. So, as you have been told, first we draw a line to show where we are going to cut. So we shall count from the decimal point 2 decimal places, 1, 2. After that, we shall draw the line. The line I've drawn is simply telling us that this is the number of decimals required. And then we circle the critical digit, and the critical digit is 9. So in the first question, we have been able to indicate, using a line, the number of decimals required and circled the critical digit. In B, the solution here, the digit is 1.75137. Again, number of decimal places required is 2 decimal places. Therefore, we look at a point where we are required to cut, and that is 2 decimal places. So after the decimal point, we count 2, and then we have our line. And then the critical digit that comes immediately after the required is 1. So we have been able to show the critical digit, and we have been able to simply show where we are going to cut. In question 2, round each of the following to 1 decimal place. Round A we have 25. B we have 13.5458. So we are required here to round off these numbers to one decimal place. One decimal place. So in our solution, considering the first one where we have 25.682, the first step is to identify where we shall have our line to show where we are going to cut. So the number of places required is one decimal place. So you'll find that we shall count one decimal place and then we show with a line this is what we require. And then now we consider the critical digit. From this, you realize that the critical digit is greater than 5. So, which implies that from the required decimal place will be rounded upwards. So this one will be rounded upwards. So the answer will be 25.7 and not 6 because we have rounded up. So this is what we shall have, and it's correct to one decimal place. So you notice that one decimal place is simply counted right from the decimal point on the right, and that is what we have. For the second question, in our solution, we need to reduce this to one decimal place. What we have is 13.5458. We want to round it to correct one decimal place. So just like others, we identify where we shall have our cutting and where we shall have the critical digit. So this is where we shall be cutting, and 4 is our critical digit. So 4 is less than 5. Then if 4 is less than 5, then our answer will be 13.5, correct to one decimal place. And that means all the other decimal places that we have, or we shall not consider them here. We only take what we require. So that is correct to one decimal place. Now, in some situation, we need to be comfortable to rounding of numbers to any other number of decimal places. It's not a must that we use either 1 or 2. Irrespective of the number of places, the principle or the rule that applies while rounding numbers always remains the same. So let us look at this next question. Round each of the following to the specified number of decimal places, and the A is round correct to 3 decimal places. I have B. 0.4 two decimal places, and C we have 7.5. This is what we have. So we are to round off, we are to round 18.347 to 8 to 3 decimal places, 0.43917 to 2 decimal places, and finally 7.59967 to 3 decimal places. In our solution, we shall approach each one independently. So let us look at the first one. We are going to consider 18.34728. We require 3 decimal places. So from here, we shall count our number of decimal places, 1, 2, 3, then bring in our line, and then we look at our critical digits. And our critical digit this time is less than 5, is less than 5 because it is 2. Therefore, it will be rounded down. We do not need to round this one up, so our answer becomes approximately 18.347. Note that our critical digit was less than 5. So it gave us simpler work. We simply settled on 3 decimal places and left the other decimals out. Let us look at the second question, which is 0.43917. So 0.43917 correct to 2 decimal places. Now, what we have here, as usual, the number of decimal places counted should be counted right from the decimal point. So we shall count our first decimal point is 4, second decimal point is 3. We bring in our line and look at the critical digit. Our critical digit is 9, and 9 is greater than 5. This 9 here is greater than 5, which implies that we shall round off 3 upwards by 1. So the answer becomes 0.44 here. This is correct to 2 decimal places. So note that we have 4 because we're considering the critical digit, which was greater than 5, we rounded up. For the last one where we are supposed to round 7.59967 to 3 decimal places. Now I want you to be very keen here. This we consider 3 decimal places. As you see, the first decimal place is 5, then 9, then 9. So which implies that this is the required. I've shown with a line. Then the critical digit we have is 6. 6 is our critical digit, and 6 is greater than 5. So we shall round up. Now, when we round up here, I want you to be very keen here. We have the last decimal point as 9. So when we round 9 upwards, it will be 10. So which means that we cannot have 10 written in the same position of a single digit. So we shall carry again 1 to the next place value. So we shall have this one as 10. We carry 1 there. 1 added to 9 again is 10. We can't have 10 at the same point here, so we have a 0. Carry 1 to this part. Then 1 plus 5, it becomes 6. And then decimal point is here. You have your 7 that way. Now, this should be our answer correct to 3 decimal places. A point to note. You notice that we have only 7.6. Why have we maintained 2 zeros and yet we find them insignificant? Now, because we are required to give 3 decimal places, then we need to remain with those zeros so that we can be able to count the number of decimal places to 3. So these zeros at this particular time are very important. At this point now, let us bring in 2 areas. We have seen the issue about fractions. We have also been able to look at decimals. Now, I want us to bring the 2. I want us to look at both decimals and fractions conversion. Now, as we saw earlier on, both decimal and as we saw earlier on, both decimal and what we have like fraction, both of them represent part of the whole. So we have seen earlier on that when we look at decimals and fractions, both of them represent part of a whole, which means that if we don't represent part of the whole as a fraction, we can still do it as a whole. So we want to look at conversion of decimals into fractions and fractions also into decimals. So first, let us look at converting decimals into fractions. Converting decimals into fractions. We shall use the knowledge of place values as we saw it in our previous class. And this particular time, if at all the denominator is a power of 10, then it becomes much more simpler. Let us look, for example, if we have a number like 0.25, you find that this one is equivalent to, when you look at the place value, 2 represents tenth, while 5 represents hundredths. So this one is equivalent to 25 hundredths. 25 hundredths, which is the same as 25 over 100. But because we are converting, it is very important that you keep your answer in a most simplified state. So you simplify as much as possible. And you realize if you simplify this, you'll get 1 over 4. So we've been able to simplify this. It has been easier to simplify simply because what we had here was simply in the hundredths. Hundredths when you look at the place values. This one here is tenths, and this one here is hundredths. The hundredths. So this one is which is going to determine what we require, and that's why we are able to say this is equivalent to 25 hundredths, which can be written this way, and when you simplify, you have a quarter. How about when we are to convert it the other way around? Maybe we want to convert fractions into decimals. For fractions into decimals, it will only be easier when also the denominator is the power of 10. For example, if we have 37 over 100 and we are asked to convert this into decimals, it will be easier because the denominator here is a power of 10. So we look at it and see, how do we represent this? You realize that this is equivalent to saying 37 hundredths. In our place values, We shall stop at that point, and we always know after the decimal point, we have the tenths and then hundredths and so on. But for this case, the last one is hundredths, so the 3 will be here, 7 will be here, and that's where we have our 0. So to convert this is simply changing it into this one directly by looking at the number of the denominator zeros that we have in the denominator. It is the power of 10. And when we have the power of 10, it is much more simpler. We look at what does it represent. Is it a tenth, hundredths, thousandths, or whichever? Then we come and agree. If that is the case, then the number we have represents the place value when we multiply, and that's what we have. As we can see here, it's simply the same as 37 multiplied by 1 over 100. That's why I'm saying hundredths. So to convert fraction into decimal is not that difficult. But what if the fraction we have, the denominator is not power of 10? If the denominator is not power of 10, for example, 2 over 5. Convert 2 over 5 into decimal. Now, 2 over 5, we may not be able to convert it because we have only converted a fraction which had a denominator as power of 10. For this particular case, we require to find an equivalent fraction whose denominator is a power of 10. So we need to find an equivalent fraction to 2 over 5, but whose denominator is a power of 10. And when we say that, looking at 2 over 5, this 5 is what is going to determine what do we require to multiply by so that we can get a denominator which is a power of 10. You'll notice that the easiest one is to multiply by 2 so that we have the power of 10 here as 10. So multiply down by 2 and the numerator also by 2. Then you'll have 4 over 10. Now, from here, it is simple. This is the same as saying we are having 4 multiplied by 1 over 10, or 4 tenths. And when you talk about 4 tenths, this is 0.4. That is immediately the first place value after the decimal point on the right. Now, it's not only those methods while converting a fraction into decimals. There is more methods which we need to use. Now, take for example, a number like 5 over 8. We are to convert now, the most general method that is mostly used in this is simply a division. 5 over 8 is simply the same as 5 divided by 8, which is 5, and then we are dividing by 8. See, using the long method, 5 divided by 8 is not possible, so we have a 0 point, then we bring in a 0 here. So 50 by 8 will give us, when you divide, it will give us a 6. Then 6 times 8 is 48. When you subtract, you remain with 2. Again, we haven't exhausted, so we shall bring down a 0 here. We don't have a digit there, so that we have 20 divided by 8. It goes 2 times. 2 times 8 is 16. When you subtract, we have a 4. You will bring another 0 here. 40 divided by 8 is 5. 5 times 8 is 40. So you'll find that we have exhausted. So then it means that 5 over 8 is the same as 0.625. Now, this method is the one that is most commonly used and it can convert any digit, any fraction that you have. This is the right method to go by. However, there are situations when you will find that you are dividing, but you are not able to end. You keep on dividing, but there is still digits coming in that we keep on working on them. What are we trying to say here? I want us to look at such situation which we call recurring decimals. Now, recurring decimals are decimals with a repeated pattern. Now, how do we find such? Now, if this is the case, then how do we handle it? Let us take, for example, just a simple fraction, 1/3. As you have seen earlier on, to convert this is the same as 1 divided by 3. I want us to use the long method. You'll find that when you have 1 divided by 3, we have a 0. Then 0 comes here, the decimal point. This one goes here 3 times. You bring down, you'll get 9. 1, you bring again a 0 here. So you'll see, you realize it's 10 divided by 3. Again, it is 3, which gives us 9. When you subtract, you have 1. You bring another 0 down here. 10 divided by 3 again is 3. It gives us 9. Now, what are we noticing? It is endless, which means 1/3 is the same as 0.3 repeated. So we have a repeated pattern of 3, 3, 3, 3, and so on. This is what we call a recurring decimal. And a recurring decimal, because with these 3's are endless, so we can indicate using a dot, like 0. This is approximately 0.3, and the number that is occurring is a 3, so we put a dot, or we can simply say 0.3, and those numbers recurring, we use a dash. So this one tells us that the digit 3 is recurring, or the digit 3, when you use a dash, is recurring. Another example of a recurring fraction a recurring decimal is, if you are to convert 13 divided by 11, you can use your calculator, and if you use that, you'll find that this is the same as 1.1818, and so on. So 1 and 8 are recurring. So you cannot just say it is 1.18 and have one single dot there, because 2 digits are recurring. So I'll have this one, a dot there, and a dot here. Or I'll simply say 1.18, and then I put a bar to enclose both 1 and 8, those 2 digits that are recurring. So when you see this, automatically you'll know that they are recurring. Another one, when we have more figures recurring, let us look at 12/7. When you use your calculator, when you divide, you'll find that 12/7 is the same as 1.7142.8. And so on. So, which decimal places are recurring? 1.714285. 714285. So you'll find that about 6 digits are recurring. So for this case, you'll only indicate very easy. If you want to indicate the recurring, you'll say it is 1.714285. And then the first digit to the last digit of the pattern that is recurring, you put a dot. If you don't want to use this one, you can simply say it is 1.714285. And then from the first decimal to the last one, you put a line. Again, this one means that the digits, the 6 decimal digits that we have there are recurring. So we can be able to convert a fraction as much as it may be recurring, but we know how to write it. We should be able to write it in this manner. Let us look at worked out examples. So question 1. So convert the following decimals into fractions, and they should be in their simplest form. So we have the first one 0.239, and the other one we have 10.35. So in our solution, as we saw it earlier on, we are going to use the place values and identify where we are going to arrive at and the furthest we can go. Now, this 0.239 is equivalent to 239 what? This is tenths, this is hundredths, this is thousandths. So this is 239 thousandths, which you can simply say 239 times 1 over 1,000, or 239 over 1,000. So this is the situation that we have. We've been able to change this into a fraction simply because we are able to know the number of the place values and what it stands for. It is 1,000, so we just say that 0.239 is the same as 239 thousandths, and that's what gives us the fraction here. But if this can be simplified further, you look at it, if it can be simplified further, you simplify to the simplest form. But for this case, that's where we stop. Let us look at the second one here. As we said earlier on, a number that comes before the decimal point is a whole number. So the 10 is a whole number. And our main concern is about the digits after the decimal point. So already here, from here, we know 10 is a whole number. Now, the 0.35, as we have seen earlier on from the place values, this is the same. 0 is the same as 10. This one is 10 plus 0.35. But 0.35 is the same as 35. Now, this is tenths, this is hundredths. Is the same as 35 hundredths. Which is the same as to say 10. We are taking 10 plus 35 over 100. So this simply gives us what? 10 and 35 over 100. But is that mixed numeral in its simplest form? No, we need to simplify it further because that 5 and 100 have got a common factor. If it has a common factor, then we should be able to simplify. You'll get now you have 10 and 7 over 20. By 5 is 7, by 5 is 10. So when you convert 10.35 into fraction, you'll be having 10 and 7 over 20. Question 2. Question 3. Yeah, question 2, we have convert the following fractions into decimals. 1, 17 over 100, B, 5 and 3 over 5, and C is 7 over 12. Convert the following fractions into decimals. Now, for the first one, 17 over 100 is the same as 17 multiplied by 100, or 17 hundredths, which is the same as simply saying 0.17. That's why I'm saying this is the same as 17 hundredths. So the answer is 0.17. That's what it simply means. For the second one, where we have a mixed numeral, we have 5 and 3 over 5. Take note that a decimal and a fraction represents part of the whole. So the whole, this side, we have no problem. That is a 5, is a whole. But what our interest is this other side where we have 3 over 5. As we saw earlier on, it is easier to simplify, to convert a fraction when the denominator is a power of 10. So I wish that we simply find an equivalent fraction of 3 over 5. And to get equivalent fraction, so we need an equivalent fraction. So we shall say that 3, we multiply here by 2, multiply here by 2, which gives us 6 over 10. Then we find that 6 over 10 is an equivalent fraction to 3 over 5. So if that is the case, we haven't changed anything, then what we have here is 5 and 6 over 10, which is the same as 5 and 6 tenths. And 6 tenths is the same as 0.6. So our answer here will be 5.6. Now note that 5 is the whole number here, and 0.6 here is a tenth. Place value is in the place value of tenth. That's why we are calling it 6 tenths. For us to arrive here, we looked for an equivalent fraction that is equivalent to 3 over 6 by multiplying the numerator by 2 and the denominator by 2. We got 6 over 10. So 6 over 10 is the same as 6 tenths, and 6 tenths is the same as 0.6. That is how we arrive at the answer as 5.6. For the last one, 7 over 12. Now, 7 over 12. This one requires us to use the normal long method. It is the same as 7 divided by 12. When you divide this, you can use your calculator or whichever gadget that you have. You'll find that what you get here is 70 divided by, that is 70 divided by 12, you'll get 5, which gives us a 60. When you subtract, you get a 10. You bring another one, you'll get an 8, which gives us 96. So when you work out this, you'll find that 96 will give us 4. Bring a 0 here. 12, 14 to 12 is 3. Gives us 36. 4. Again, this one gives us 3, which is 36. Again, 4. What are we realizing here? You must have noticed that these 3 seem to be recurring. It is endless. So we can simply now agree that 7 over 12 is the same as 0.58333 recurring. And as we saw earlier on, how do we write a recurring decimal? So this one is the same as 0.583. The digit that is recurring is the one we give a dot. So 3 is recurring. That is how we arrive at our answer. If you didn't want to have it like this, it is simply 0.583, where 3 is recurring. We use a bar. So that is it for today about converting fractions into decimals and converting decimals into fractions. Thank you.